Okay, we're going to start off with our bell work today. This is going to be a review of last time's lesson 10.1. 10.1 was permutations and fundamental principle, counting principle. So this first problem can actually be done with the fundamental principle of counting or a permutation. It says there are 5 finalists in the Mr. Rockhill pageant. In how many ways may the judges choose a winner and a first runner-up? Okay, if you did this as a permutation, you would just say, well, there's 5 people to choose from, and order matters because a winner and a first runner-up, order matters there. The winner wants to win, right? So 5 permutation 2, you could do that on your calculator, and you could get, not 60, that one turns out to be 20. You could do that on your calculator, and you'll get 20. And then you could do that as a counting principle, meaning first spot could be, we'll call the winner first place, and then the second spot would be the runner-up, which we'll call second place. So there's 5 people, somebody wins, so this kind of like goes back to the license plate problem, you can't repeat, somebody wins, so now there's only 4 people to choose from for second place, and so the answer is 20. So you can do that either way with a permutation or a combination. Okay, the next one. A multiple choice test consists of 15 questions, each permitting a choice of 5 alternatives. In how many ways may a student fill in the answers if they answer each question? So this is the counting principle again. So for question number 1, you have 5 choices. For question number 2, you also have 5 choices. Question number 3, you also have 5 choices. Question number 4, you have 5 choices until, same thing happens until you get down here to question number 15 and you still have 5 choices. So if you multiply all that out, you're going to get 5 raised to the 15th power. And we'll just go ahead and leave it like 5 to the 15th. Okay, this last one. How many distinguishable permutations are there in the letters of the word greet? So remember, there's 5 letters, so we're going to do 5 factorial divided by, and the only 2 that we can't tell the difference between are the 2 e's, so we'll do 5 factorial divided by 2 factorial. Go to your calculator and you can do that, and that turns out to be 60. Okay, so that's a review of everything on the 10.1 lesson. Fundamental principle of counting, permutations, and distinguishable permutations. Okay, today is going to talk about combinations, and in combinations, the order doesn't matter. So that would go back to like the example I used last time. If I'm looking for a committee and I just want to pick 5 people on my committee, I don't care that they have titles to them, that it's just 5 random people, then that would be a combination. Permutation would say, well, of that 5 committee, if I started saying I've got a president, a vice president, a secretary, a treasurer, a historian, when I start putting labels on them, order starts to matter. So combinations, order doesn't matter on the outcome. In probability, we do a lot with cards. So here I've put a deck of cards in case you didn't know how cards work. There's 52 cards in a deck. There's 4 suits. You've got diamonds, hearts, spades, and clubs. Half the deck's red, half the deck's black. Each suit, so these right here are called suits right here. This is your suit. Each suit, diamonds, there's 13 cards. Your face cards would be your jack, queen, and king. Those are your face cards. Just so you'll kind of have an idea when they talk about questions about those. Okay, so this first one says, how can you choose 5 cards from a 52 card deck? Okay, so order there doesn't matter, guys. We're just taking, it's like I took all 52 cards, I dumped them in a bowl, and I'm just going to take 5 out. I don't care, I'm just taking 5 cards out. So I could do that as a combination. So if I'm going to use my formula here, notice the only difference between the combination and the permutation, let me write up what permutation was last time. Very similar, except that permutation just did n minus r. It didn't do divide by r factorial. Okay, so very similar formula. So we're going to do 5 cards. So we've got 52 cards to choose from, and we're going to choose 5. So if we're going to use our formula, we're going to say that's 52 factorial divided by 52 minus 5 factorial divided by 5 factorial. Okay, and then you can go to your calculator and figure out what that number is. So it's 2,598,960. Now, instead of typing in the formula every time, you can just use your button. You could have done your combination button is right by your permutation button. So hopefully you know where the permutation button is from last time. So combination, you would just do 52, hit your combination button, 5. That would give you the same answer. A lot faster than doing the formula. Okay, how can you choose 5 cards the same color from a 52 card deck? Okay, well this one, if you want to choose 5 cards of the same color, there's 26 cards in the deck that have the same color, and you want to choose 5 of them. Once again, order doesn't matter. I'm picking only 5 cards. It's like I'm throwing all the red cards in a bowl, or I'm throwing all the black cards in a bowl, and then I'm taking 5 cards out. Okay, the problem is you also have to have a choose a color. So on this one, we're actually going to do 2 things that we're going to multiply together. We're going to take 2 combinations. The color, there's no order to the color. Order doesn't matter on what color I pick. I'm just picking between black and red. So there's 2 colors. I have to pick one. So that's what we're going to type in. We've got to pick a color first, and then we're going to pick 5 of those cards out of that color. So if you type that in your calculator, you're going to get 131,600 or 5,060 or 560. 131,560. That's our answer. Okay, so when you're working with events and you want both events to happen, so over here, the one that we just did, we wanted to pick a color and 5 cards. We're going to multiply those. That's why we kind of multiplied those. So we multiplied those 2 together. If I wanted to pick one event or the other, so this would be saying A or B, then we would be adding the event. So that would be over here if I wanted to pick a color or choose cards. That would be a different story than pick a color and choose cards. So let's see how that works. So here we go. We've got William Shakespeare. So William Shakespeare wrote 38 plays that can be divided into 3 genres. Of the 38 plays, there are 18 comedies, 10 histories, and 10 tragedies. How many different sets of exactly 2 comedies and 1 tragedy can you read? Okay, so we have to pick how many different sets of exactly 2 comedies. So we got to pick 2 comedies and 1 tragedy. So notice this is an and, so that means we're going to multiply these 2 together. So the order doesn't matter of the comedies that we read. There's 18 of them, and I need to read 2 of them. So I'm going to choose combination and not permutation. And I have to choose a tragedy. So there are 10 tragedies, and I'm going to read 1 of those. So if I do that, then I'm going to end up with 1,530 possibilities. Those are our outcomes. Okay, how many different sets of exactly 3 tragedies or 2 histories can you read? Okay, so now this one's an or. I can do the 3 tragedies or 2 histories. So the tragedies, there's 10 tragedies. I need to do 3 of those. Or out of the 10 histories, I need to read 2 of those. And come up with that, and there would be less combinations. There would be 165. So we could type that in our calculator to get that answer. Okay, the last one, a little bit harder. We need a little more room here. Let me scroll down. How many different sets of at most 3 plays can you read? So keyword here says of at most 3 plays. So if your English teacher told you you had to read at most 3 plays, I being the not really into reading Shakespeare, would probably pick 0 plays. Would that be okay under at most 3? Yeah, the teacher didn't say, said at most 3. Well, 0 would count. So I could do 0 plays. Okay, so that's probably not what the teacher meant. So I guess I'll read one play. That still works. Somebody really likes Shakespeare, so now maybe they're going to read two plays. Um, and somebody just really, really loves Shakespeare, so they're going to read three plays. Do all of those scenarios meet the parameter of at most three plays? They do. So what you have to do is you have to figure out each of those individually, and then you've got to decide, is this an and or an or? Well, I'd say this is an or situation. I'm going to read 0 plays, or 1 play, or 2, or 3. So when I go through and I work that out, you've got to do 38 combination 0, and then this one is 38 combination 1, 38 combination 2, and then 38 combination 3 plays. So we're going to add all of those together and type that in your calculator, and I think you should get 9,178 if you type it in correctly. Okay, here's another one. During the school year, the girls' basketball team is scheduled to play 12 home games. You want to attend at least 3 of the games. How many different combinations of games can you attend? Okay, you want to attend at least 3 games. So at least 3 would mean that you go to 3 games, 4 games, 5, 6, 7, 8, 9, 10, 11, or all 12. That's what could happen. Okay. So how are we going to set that up? Well, there's 12 games. So if you chose this one of going to only 3 games, that would be 12 combination 3. If you chose to only go to 4 games, then that would be 12. Oops, that's a little 12, not a big 12. Let me write that better. This is your 12 combination 3, and then 12 combination 4, plus 12 combination 5. We could keep going. Combination 6, plus 12 combination 7, plus 12 combination 8, plus 12 combination 9, plus 12 combination 10, plus 12 combination 11, plus 12 combination 12. And we can add all those up because it's going to be one or the other, right? I'm going to go to 3 games, or I'm going to go to 4 games, or I'm going to go to 5 games, or I'm going to go to 6 games, or I'm going to go to 7 games. So we're going to add all those up, type that in our calculator, and we're going to get 4,017. Sometimes it might be easier to do the opposite of what you wanted to do. So for example, there were, let's see, let's count these up. How many of these did we have? We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possibilities that could work. So that would mean then that we probably had 3 possibilities that didn't work. So it might be a shorter problem if we figured out total possibilities. So if we did the total outcomes and we subtract the outcomes that we didn't want. So let's say we'll say the not outcomes. Oh, well, I shouldn't have erased that. Outcomes we didn't want. So that might be a shorter math problem to do. This one's a little bit harder to figure out. The total outcomes is that there's 12 games and there's 2 choices. Either you go to the game or you don't go to the game. So the total outcome is 2 to the 12. That's basically what can happen. And then you could subtract out the choices that you didn't do. So for example, if you chose 0 games, and if you chose 1 game, and if you chose 2 games. Those are the scenarios that didn't work. So if you do that math problem, you should still end up with the same 4,017. Conceptually, I think it's easier for students to do the first one that we did, this top scenario right here like this. This one makes more sense to them. Mathematically, this one, second one is probably shorter. I don't care which way you do it. Like I said, conceptually, most students find the top method a little bit easier than the bottom one. All right, we'll try some more with some cards now. So what you've got to remember, it says find the number of possible 5-card hand. That means you're going to have 5 cards in your hand at all time, okay? That contain the cards specified. So the cards are taken from a standard 52 card deck. So we're going to do 5 face cards. So nothing too complicated about that. There's how many face cards in the deck? There's 12 of them, and you're going to choose 5. And so type that in your calculator, 792. You want 4 kings and 1 other card. Okay, so this is an and, so we're going to multiply. So in the deck, there's 4 kings. You're going to choose all 4 kings. And you want to choose 1 other card. Well, there's only 48 cards left now because you took out the 4 kings, and you have to choose 1 of those. So all of these are all combinations because order doesn't matter here. We're just randomly picking these cards. All right, 1 ace and 4 not aces. A lot of times in statistics, they will use the word not. Just means the opposite of you go on aces and no aces. Okay, so they just use the word not. So 1 ace, if I was going to pick 1 ace, there's 4 aces in a deck. I need to choose 1. And then 4 other cards is what I'm going to have to choose from because I've got to have 5 cards in my hand all the time. There's 48 cards left. And I'll end up with 778,320. Okay, we're going to do 5 hearts or 5 diamonds. Well, there's 13 hearts. You got to choose 5 of them. Or there's 13 diamonds, and you got to choose 5 of them. And that will turn out to be 2,574. Okay, now we want to choose, oh, these are going to get to be the harder ones because we're going to do, it's not one scenario, it can be multiple scenarios. Okay, we're going to do at most 1 queen out of the 5 cards. So if you're going to have at most 1 queen, your possibilities are you could have 0 queens, or you could have 1 queen. So to figure that out, let's do the combination for 0 queens. So remember, we always got to have 5 cards. So there's 4 queens in the deck, and I'm going to choose 0 of them. And I've got to pick 48 cards are left to choose from, and I've got to choose 5 other cards. And then here we've got to choose at least 1 queen. We're going to do out of the 4 queens, we're going to choose 1. That's a combination, right? Because order doesn't matter. The C doesn't stand for choose, it stands for combination. Times, and now there's still 48 cards left in the deck, but I'm going to only pick 4 of them because one of my cards is a queen. So all you've got to decide is out of those 2 combinations, am I going to multiply them or am I going to add them? I think you're going to add them because it's scenario number 1 of 0 queens, or it's scenario number 2 of 1 queen. So there's 2 different scenarios. So you're going to want to add those because that's an or. Type that in your calculator, and you're going to end up with 2,490,624. Okay, and then the last one, at least 1 spade. So once again, there's a long way and a short way to do this. I'm going to do the long way because I feel like it's a little more straightforward. People tend to understand this one a little bit better. So what are our possibilities of at least one spade? Now remember, we're only choosing 5 cards. We're not picking all the spades. We only need to have 5 cards in our hand. So I could have 1 spade in my hand. I could have 2 spades, 3 spades, 4 spades, or 5 spades. That's what could happen if it's saying at least 1 spade. Okay, so if I'm going to do at least 1 spade, that means there's 13 spades in a deck. So out of 13, I'm going to have one of those. I'm going to use 13 combination 1. So remember, combination order doesn't matter. It's like I dumped all 13 spades in a bowl and I just picked one out of the bowl. Okay, now out of the cards left, since I'm talking about spades, there's only 3 other suits to choose from. And so out of that, there are 39 cards left, because out of the 3 other suits, that would be 39. 13 cards in each suit. And I need to choose 4 of those. Okay, for 2 spades, there's 13 spades, combination 2 times, and then there's still 39 that I'm choosing from, but now I only need to pick 3 of those cards because I've already got two spades. Okay, if I'm going to do 3 spades, there's 13 spades, combination 3 times 39 combination 2, because I only need 2 other cards out of the rest of the deck. And then 4 spades would be 13 combination 4 times, there's still 39 other cards to choose from, but I only need 1 because I only have to have 5 cards in my deck, or excuse me, in my hand. And then 5 spades, there's 13 spades, so 13 combination 5 times, out of the 39 cards left, I'm going to do a combination of 0. I don't need any of those because I already have 5 cards in my hand. Okay, so once again, you need to make a decision. Are you adding or multiplying those scenarios? Since they're individual scenarios, one or the other could happen. We're going to add all of those scenarios together. So when you add those, you're going to end up with, I think it's 2,023,203. 23,203. 2,023,203. Okay, what about the other scenario where we use the ones where we pick the scenario that we don't want? So that would be like all cards. So that's your total possibility. So total outcome. So that's your total outcomes minus the combination of no spades. So that would turn out to be, total outcomes would be 52 cards, and I need to choose 5. And then there's the scenario where I don't pick any spades. So there's 13 spades. I don't choose any of them. So it's a combination, remember, because order doesn't matter here. Times 39 cards left, and I have to pick 5. Those 2 scenarios should give you the same answer. That should be the same thing as that. All right. That's combinations.